Okay, we got electrical basics here. And we got electrical basics, and we're going to be looking at this. And what we can do is, I'm going to have to walk back and forth to go over it because I don't have my clicker with me today. I guess I could probably hook that serial interface up with that thing here and use that for a clicker, but not do that.
In your pocket, in your pocket, in your pocket, in your pocket.
No, laser. No, I was talking about the changeable slides. Okay. Now I may have to pause from this because I think Patrice Owens is coming here to get a work order made in a minute. Basic electricity, chasing sparks. I've gone through this. Everything that's got substance has got atoms. We're going to spend a lot of time on each slide, but this is the way I do PowerPoint, right? All atoms have negatively charged particles called electrons. So you got to remember, it's important. Electrons are negatively charged. And they're going around a central core, which is the nucleus, and that's believed to be positively charged. Now there is, incidentally, after you get through this, you may want to go back and reattempt the electrical pretest if it smacked you around. How did you do on that, by the way, the electrical pretest quiz? Yeah, he did about the same you did, so you don't say it or something. All right, but now as you go through these, you're going to see them, man. We'll go through when we're done here. We got neutrons, we got protons, we got electrons. Protons have a positive charge, neutrons have no charge, and electrons have got a negative charge. Electrons in the inner orbit are bound electrons. So you got two orbits there. The outer orbit is the ones that aren't bound, they're free electrons, and the ones on the inside are electrons that are bound. The ones on the outside are the ones that move. The valence ring, if there's 3 or less, now this is important too. If there's 3 or less free electrons in the valence ring, the material makes a good conductor. Right? You got that? What's a conductor? Something that will carry electricity, right? Yeah. All right, so if you got copper, lead, any kind of metal.
So many is more than 3, right?
Yeah. If it's got, you know, if it's only got one, it's like gold or something. All right, gold and copper only got one electron in their valence ring, so they really conduct well. The material with 4 electrons is a semiconductor, such as the materials used to make diodes and transistors. They will only flow current under certain circumstances. They won't flow current just anytime you shoot used to them. All right? Okay? A valence ring with 5 or more electrons makes a good insulator. Glass, rubber, air, wood. Now let me ask you this. Let's say that I'm beside the road and I forgot to put anything in the truck to check and see if I had spark. And I take a piece of heater hose that happens to be laying in the back of my shop truck that the guys come to pick me up after this car I'm working on is quit. And I'm going to take my pocket knife and I'm going to shove it up in a piece of heater hose, and I'm going to use that piece of heater hose to insulate while I check for spark. How's that work? In other words, I'm going to take a piece of heater hose and I'm going to slide my pocket knife. I can find my pocket knife in here. Maybe I brought it this morning. Probably didn't. But anyway, I'm going to slide that piece of heater hose over that, and I'm going to hold on to this piece of heater hose. I'm going to stick the tip of that knife in a spark plug wire, and I'm going to hold it over close to the heater. I'm going to spin it over, and I'm going to see if I get a spark. Now, is that a good thing to do?
No.
Why?
Because you're still holding the knob if you're in it.
No, I'm holding a piece of hose. The knife is stuck up in the piece of hose. The knife is in the piece of hose.
Oh, so it's going to be stuck in there. You're not going to.
It's going to be stuck in the hose. I'm holding on a piece of hose.
Yeah, that'll work because rubber's insulated.
Seems like it would, but there's little fiberglass strands in the hose that will carry that juice, and it will light you up.
Oh, cool.
I mean, I've seen that happen before. Somebody put a piece of hose on there. It's been over, you know. Fire them up. Good. Okay. Electron theory states current flow is the organized force movement of free electrons in a specific direction. So continuous current flow in only one direction is known as DC, or direct current. If it's only going one way, that's actually DC current. What's coming out of the wall over here is what? AC current is flipping polarity. How often? How often does the polarity switch on an alternating current? 60 cycles per second. 60 cycles per second it's flipping back and forth. All right. Flow that alternates back and forth is called alternating current. That's what that's talking about. It's basically you're changing the polarity of it back and forth all the time. A good conductor is a lot of free electrons such as copper, lead, and gold. We're going to go over that just for a second. All right. Good conductors readily transmit electricity. Okay. Electromotive force is the force that causes electrons to move from one atom to another. Okay. How can I make some electromotive force? If I wanted to make some electromotive force, how can I do it? Can I do it
Magnets?
with this?
Oh.
That's a little electric motor,
Uh-huh.
and I can actually hook up to this, a light bulb to this, and I can spin it with my hand, and it'll light that up. Because I'm generating current. Inside here, I've got a little commutator with some brushes on it. I got some windings, I got these little things, and when that goes past those magnets, as that magnetic field sweeps across those windings, it creates power. And that's basically, you can actually take an electric motor and turn it into a generator. You know, if you drive this, you know, like on your hybrid vehicles, when you hit the brake, it's charging the battery. They're just switching some stuff around so that instead of the motor starting the engine, when you hit the brake, it's actually, you're letting the momentum of the car drive the motor, and then you're running that juice back into your big battery. Well, there's some pretty sophisticated electronics that make it happen, but it's really simple. Whenever, and you know, at its base, whenever you spin a motor, it makes juice. All right, so, okay, electromotive force is caused by a difference in electrical potential. It's measured in volts, and that's referred to as voltage. So, voltage is basically a difference in electrical potential. There's a lot of different ways to teach this. There's a lot of different ways you can teach this, and there's a lot of people that write stuff about it. And there's some people that don't like, you know, the way that we're teaching it. This right here came from a training course that actually, I mean, I built this PowerPoint presentation, but the principles and the way I'm using them came from something Ford published back in 1988. And it seems to work better for automotive purposes than anything else I've ever seen. And that's the reason I'm teaching it there. And whenever Lindy comes in there, make sure he gets that, but make sure he doesn't sit there. All right, so think about this. If you ever play pool, you can line up those balls and you hit this one, that one's going to take off. This is kind of the way it works. You throw an electron in here, one pops out on the other end. Got me? All right, some older cars have got the positive part of the battery hooked to ground. Caterpillar equipment, some of the Caterpillar equipment I worked on when I was working on heavy equipment down in southeast Texas, would have a positive ground. Can I take a Caterpillar pipe loader that's got positive ground, which is basically the hot sides hooked to the frame, and a Huff International pipe loader that's got a negative ground, and can I jump one of them off with the other one? Like if I'm going to use jumper cables backwards. Huh?
If you did it backwards.
No, you're still one way. If you do that, you're going to have big sparks and welding machines and all this kind of stuff. You know, there's enough power in a battery where you can hook welding leads up to a battery, put you a stick in there, and you can weld with a car battery. And just make a bead, like a welding machine, but it's DC current, but it's still weld. Because there's that much power in a battery. And you run it down pretty quick like that, but it'll work. All right, see right here? Here you got, if you don't have the two pieces of equipment touching, you're okay. You can just go positive to positive, negative to negative. But if the metal parts of these two pieces of equipment happen to be touching one another, it'll short out. See what I'm saying? I used to run into those. Okay, no production vehicle uses this configuration today. You may see it on some pieces of heavy equipment. I don't even know if Caterpillar does it anymore, but I knew they used to. Today's vehicles got the negative battery terminal connected to the block and to the ground. You're always going to see coming off the battery, you're going to see the big battery, the big terminal is going to go to the engine block or the starter. Got me? Why would we take it directly to the starter? Well, what's the most significant draw of power that you use more than anything else is the doggone starter. When you're spinning it over, you want to make doggone sure that starter's going to go ground. Well, the starter is bolted to the engine anyway. Well, what if I'm going to the engine block with the ground, but my starter happens to be dirty enough and loose enough to where it can't get a good ground? You know, yeah, you're going to have some voltage drop between the starter and the engine block if it ain't tight and there's stuff in there.
I know.
But anyway, there you go, Lindy.
Thank
Here's a little test there. All right. A positive feed wire component all originate in positive battery terminal. On hybrid vehicles, your instrument cluster and all of the stuff that you got in the dash and the electric power steering and all that kind of stuff runs off 12 volts DC. Okay, what comes out of the battery on a hybrid vehicle?
AC.
No. You don't have no battery putting out no AC. Okay, you got DC volts coming out of the battery, and it goes through a DC to DC converter, and that provides 14 volts that charges the little 12 volt battery. It may be a glass mat battery, maybe some other. But the long and short of it is, you're going to have a regular 12 volt electrical system on this car to run all the stuff like your radio and all that. You're not going to have a radio on the dash on a hybrid vehicle that runs on 240 volts or nothing like that. Basically, though, the big power that comes out of those the battery goes through a DC to AC converter, and that's basically, they call it an inverter, and every motor on that car that's driven with that high voltage, whether it's the AC compressor or whether it's your big motors in your transmission or whatever, is driven through an inverter. It changes DC to AC. See, you got that. Even the little electric water pump they have on those things is AC. It doesn't have an inverter. It works a different way, but it actually is it doesn't have a resolver like the other one does. It does have an inverter. Okay. When a switch is closed, current flows from the battery, negative post to the chassis ground through the load and switch to the positive terminal. Notice you've got a full circle there. If you don't have a full circle there, you got issues. Got me? Right. Even though the ground's got an excess of electrons, the positive post is the one that's generally guarded as hot. See, the power is actually coming, according to electronic theory, power goes from negative to positive. The current flows that direction. And they have this thing called hole theory. As this one electron moves, it leaves the hole, and so the hole is going one way, electrons are going in, or whatever.
That's why you want to use the negative side of the battery whenever you're working on anything, correct?
Well, that's part of it. Another reason you do that, when you disconnect the negative side of anything, you don't get nearly the spark you do when you disconnect the positive side. And a lot of the times you're going to see stuff that's negative side switched, so that you'll wind up with a situation where when it's negative side switched, the transistor or whatever is doing it doesn't have to work quite as hard. However, with that said, you'll see some of your Nissans and Asian-made transmissions particularly will have their solenoids hardwired to ground, and the engine controller or transmission controller will hot switch those solenoids. So, and old Jeep Cherokees like 87 to 90 had fuel injectors that were switched on the positive side, which is weird. They had them hardwired to ground, but they were operated backwards to what you're used to. Most of them, you got a ground to switch it because it's a little easier on the circuit. But the other reason you disconnect the negative battery terminal, like you said, as long as you leave the negative battery terminal hooked up to the battery, that whole car is grounded. If you drop a wrench and it happens to land on the body and lay across the positive post, you still got a short, don't you? Even if the positive cable is unhooked. So basically, if you disconnect the negative side, you're not going to have a short. There's no way you can have. Right? Okay. All right. Electron theory supposes the current flow to be from negative to positive. Conventional theory supposes the current flows from positive to negative. There are questions on your CDX pretest about that. So everybody in here needs to get that electroelectronics pretest out of the way. It's kind of like the one you took for foundation and safety, but it's a pretest, and I've tried to make it not quite so long.
Is that the one that was timed?
Huh?
Is that the one that was timed?
I don't think so. The one that's timed is going to be the one that's actually is going to count for a grade, but I could be wrong. Maybe. It may be time. Yeah, I couldn't think of it. Thus, the current in an automotive circuit is usually traced from the source to the load to the motor and then the ground. If I've got something I'm trying to track, and I want to see if I'm, like something doesn't work. I've got an issue that don't work. I've got a light that doesn't work. And a lot of people don't even think about this. We talk about voltage drop test whenever you're basically going to go from your source of your voltage to the hot side of whatever component you're looking at. Like, if your headlight bulb, the power goes from where? From the battery, it goes to the switch. From the switch, it goes to the dimmer switch. From the dimmer switch, it goes to the headlight bulb. That's a lot of connections, isn't it? Well, most people don't even think about that. But if you've got, let's say that you've got a light that's dim, right? I mean, the headlight is dimmer than the other one. How you going to find that? It's not always the same thing. On some of the older Toyotas, they had a different fuse for each headlight. If you pull one fuse, the headlight would still be on, but it'd be dim. Which is interesting because you wouldn't ever expect a blown fuse to make a headlight be dim, but it will sometimes. Okay, so what you do is you take your meter, you put it on your 20-volt scale. The hot side of that light that's lit up when it's turned on, you go to the positive battery terminal, and you're measuring, whatever voltage you measure there is what's being lost between the positive battery terminal and that light bulb. Okay, and then if you find out, oh my goodness, I'm dropping 3 volts here, there's no wonder, there's no wonder on that. I have no idea who that is. Hello? Yeah, this is Richard. Yeah, yeah. Yeah, we gotta get your financial aid straightened out too, and, we can try to straighten out your truck if you can get it over here. Drive slow, you know? Mhm. Well, we probably ought to have a look at it for you. But anyway, right now I'm talking in the classroom.
Right now,
But get over here as quick as you
$700
can, we'll try to get your
so I can
financial
walk that
stuff
far.
straightened out when you get over here, and we'll also look under there and see if you're gonna have some serious problems with your front end. Okay? Yeah, drive slow. But anyway, all right, let me finish what I'm doing, and we'll talk a little later. All right, so, that's another guy. All right, now then, what I was gonna say was, basically, when you track your car out, what do you do? Let me ask you this, something don't work, what's the first thing you check?
You look for,
Battery.
Let's go cheap and easy, man.
I check.
Everything else is working, but I've got a particular component that's gone dark on me.
fuses.
Fuses are the smartest and easiest thing to check, right? It's quick and easy, no problem. So go check your fuses. And some people get confused if they go to the fuse panel with a test light, you know, you got a little exposed back each fuse where you can touch it and let it light up. They'll say, I've got a bunch of fuses here that aren't lit up. Well, don't worry about those unless one of them is the one that's feeding what you're checking. I mean, you know, don't get sidetracked, because some people say, I don't know. I'll tell you what will mess you up. I was working on a Thunderbird that the cruise control wouldn't work on in 1984 at Lincoln Mercury dealership, and it was smacking me around until I realized somebody had pulled a fuse. You know, I mean, because there's a lot of them you'll see, like on my pickup truck, there's fuses, places that don't have fuses in them. And if you know what I'm saying, you better make sure that you know which fuse you need to be checking instead of just looking at all of them. That's why they got little, you know, legends on there a lot of times. On some vehicles, though, you may have to look in the owner's manual if you've got one. But best way to look at it is on all that. I don't never get the owner's manual out on one. I mean, a lot of people flip through the owner's manual like there's a person driving a car, you know. But anyway, make sure that you got a fuse. But you're going to start from positive, and you're going to work your way to the component, and then you're going to check ground usually. The ground is the dark side. You remember Darth Vader? You don't know the power of the dark side. Now, I'm going to tell you something else about checking the ground. A lot of these people that teach at colleges and stuff will say, don't ever use the test light on the car because you always need to use a meter. Well, that's a bunch of hooey, because you can be checking with a meter and read what looks like good voltage there, but it won't do nothing. And so basically, if you go to the places, these Top Gun guys that teach at KC Vision and places like that, they will tell you if you've got a component that's not working, you need to take a light that draws, 4, 5, 6 amps, which is like a headlight bulb or something, and see if use that, hook your headlight bulb up to hot, and use the ground that's supposed to be feeding this component to see if it'll burn the headlight bulb. I had a situation on this Ranger out here. I got that Ranger, turn it on, no fuel pump operation, no fuel pressure, all right? I did not plan this bug, all right? So I go over here, and I'm checking, I unplug the fuel pump, got the bed took off and got it back out of the way, unplug the fuel pump, and I get my little test light, my little regular test light like I use, low impedance test light, and I hook it up, and it fires up. The test light fires up. Well, I got power there. It should work. So I pull the fuel pump out. I put it on the bench. I test it on the bench. I need a bad fuel pump. What's up with this? And so I got my headlight bulb. The headlight bulb I got wired in this plastic thing with this little wire on it. And I hooked the headlight bulb up between the ground and the power. It would not burn the headlight bulb. The headlight bulb pulls about the same amount of current as the pump does. Right? Which was about 6 to 8 amps whenever it's pumping fuel. 1.5 amps when it's not. See what I'm saying? So this thing would not burn that headlight bulb, but my test light showed me there was power there. You see how you can fall in trouble like that? I mean, you see where I'm going with that? You need to make sure there's enough current available there to operate that thing. We'll talk a little more about that. All right. So, all right, let me get this right here. Okay, the positive and negative plates are immersed in electrolyte composed of water and sulfuric acid.
Yes.
You go, boy. And I tell you what, log into your CDX and go through your pre-test on engine performance. Okay? Can you do that for me? All right, that'll get you. Because he's already took electrical, and I don't know why I was picking him up clean. All right. So, when the battery's charged, there's a chemical reaction on the plates that results in an excess of electrons on the negative side of the plate. So basically, you're moving all the electrons over to the negative side, and they really want to go over here. They want to go over there really bad. All they need is a path. Okay, so how many of you guys have ever dropped a wrench and or a screwdriver and it lands and it shorts out on both posts? What happens?
So
It gets really hot.
Oh, really quick.
And it becomes the load. A jumper wire. How many of you guys fooling around in here with this thing have burned up jumper wires? I mean, and a piece of wire this long, if you got a short under your dash, and you got a piece of wire that long that gets really, really hot, it'll fill that whole cab up with poisonous smoke.
Yep.
One little tiny piece of wire will fill, and you'll think, oh no, my whole wire harness is destroyed.
I had that happen in my 79. Remember that white truck I drove?
Uh-huh.
The cigarette lighter one. I put in a cigarette lighter to light a smoke.
Yeah.
Going to work and filled up the whole cab. I was
Yeah.
glad that I had a hole in the floorboard.
Yeah, and it wasn't very bad, you know. I mean, as far as, there wasn't a bad short other than the fact that that one wire gets burned up. We had on these ignition switches that you see on these vehicles, a lot of times whenever you turn the key to the start position, your temperature light will come on to prove it out. So there's a ground that is fed to the ignition switch, and it feeds that out to some of these warning lights to make sure that they work. When you turn it to the start position, you might see a lot of your warning lights will come on just so you make sure they work. That's a prove out, they call it. We got an ignition switch for a Ranger from a parts store, and we put it in there. And as soon as we turned on the key, that little ground wire that was hooked to that switch, internally that switch was shorted, and it burned that wire up and filled the whole cab up with smoke. And we had to put another wire on there and a different switch, you know. But that switch, that wasn't the original problem. We replaced the switch for something else. But that switch was internally shorted. So those switches have got a lot of close quarters contact between all them copper strips in there, and if they ain't built quite right, you'll get a problem with them. All right, when a conductor is connected to a closed circuit, pass through the magnetic field. If you got a magnetic field and you pass this through it, and you happen to be measuring voltage, you're going to see voltage there. You can also stick a little weak little light bulb in a lemon, and it'll make a light bulb light up. All right, pay attention to your questions. Alternators, generators, and various inductive sensors, they create that. This little sensor right here is called a variable reluctance sensor on the front, a crank sensor. And every time those teeth go by there, it's got a magnet in there, it's got copper wires wrapped around it. These two wires up on either side of that copper wire, and it basically is going to create a little voltage wave if you look at it with an oscilloscope. All right. All right, electrons can move from one body of matter to another by friction. You know, how many times do you ever reach out to get out of the car and you get popped?
All
You
the
know,
time?
you know how you prevent that? Get some of that stuff, that anti-static spray, and spray the seat on the car. That'll take care of it. I mean, if you're having that problem in the winter and it's driving you crazy, keep some of that anti-static spray in there and spray it on the seat and all, you know, before you get in there, and you won't have that problem. There was a guy that came over on a Mustang. Usually on a day like today, when it's cold and dry, is when you pop somebody, right? Or you get popped whenever you reach for something. You know how many voltage that is? That's 8 to 25,000 volts. It's jumping out of your finger. Sometimes you'll see it jump a long way, like in half an inch or something, like a spark plug pop. There was a guy that came to the Ford place one time. He had a Mustang. And this guy on this Mustang says, "This thing shocks me and my wife every time we get out of it." So he got out, and when he touched it, and it was not even on a cold, dry day. It was on a normal summer day. So he gets out, he touches it, and I heard it pop a little bit. And he goes, "See, it does it every time I get out." And so I got in it and got out, and it didn't shock me. And I got in it, got out again, and it shocked me. Well, he got in it, got out again, I heard it pop a little bit. And I tell you what, I said, "You let me hold the door, and you get out, and then touch me. How about this?" That was a mistake. Because whenever he got out of there and he stuck his hand close to mine, there was blue lightning that come out of his finger that long. He just fired me up, and I was like, "Yeah!" You know, this felt like I got hit by a coil, an ignition coil. I never did figure out why him and his wife would get shot. I do know that, you know, I knew this one woman really well. She couldn't wear a watch because it would lose 15 minutes or something on her arm. When she put a watch on that was keeping good time for me, it would lose time on her arm. She just couldn't do it. And my son Matt's like that too. He can't wear, you know, anyway, one way or another. Okay, lightning. My brother-in-law took his picture, by the way, up in Tuscaloosa with his camera. All right, another form of static electricity discharging. Now, when you hear lightning, thunder follows. The sound of that spark, boom. Whenever a spark jumps from a spark plug, you hear a pop, right? That's the same sound, except it's on a smaller scale. Make sense? And why is it making that sound? Okay, it's punching a hole through the air. The air is an insulator. When the spark goes away, the air goes rushing back in there, and you hear a little, you know, when the air goes back in. Why does the sonic boom from a fighter plane? Because it's pushing the air out of the way, and when it comes back together behind it, boom, you got that, see? You know, like when they thought the plane blew up that Chuck Yeager was flying? All right. Electrical circuits right here. There's our little test light thing. That's a little test light that I actually put together with an LED in it. Electrical circuit's a complete path. Power source, load. A load is a motor or a light or anything like that. It's got a resistance. The load's got resistance and uses the power. You know, your filament in the light bulb gets hot. Your motor basically uses it to spin the motor or whatever. You got to have a ground path back to the negative source. One component necessary, you've got to have a battery. This is a battery. This is what it looks like on a schematic. This is the battery. This is what it looks like on a schematic. This is the battery. This is your brain on drugs. No, whatever. So that's what you got. All right. Automobile power source is the battery when the engine's switched off, and the alternator when the engine's running. Hey, I was going to wait until you finish. Yeah, man. I should have dropped that off. Sorry. Thank you. Right. There you go, Willie. There's your rubber ring. All right. Okay. Now then. That's a side post. And I hate side post batteries. I despise them with a passion. You can look at them and they look like it's got a good connection. You can't see. And it's very, very difficult to do a test. You know the test that's most reliable to check and see if you got a good connection on your side post? That inductive current thing that checks batteries. If you hook that up to those side posts and it reads crappy cold cranking amps and you know the battery's good, then in other words, if you hook it up to there and then you take them off and you measure the battery, it's got like 800 cold cranking amps. And when you hooked it directly to those, it's got like 200. That's about the most accurate way you can measure that. In other words, you can actually take them off and see what they look like. That's a good way to do it too. Conductors, wires, cables. They got to have, see how that one there rubbed through? They've actually got to have insulation on that that keeps them protection. They carry the current in an electrical circuit, obviously. In an automotive circuit, vehicle chassis and the engine block are conductors in the circuit. So the engine block and the vehicle chassis, you notice coming off your battery, not only do you have the big wire going to the engine block, you'll have a secondary ground wire going to the frame, and in some cases you'll have the engine grounded to the frame. Now some of the motor homes, we would have these motor homes. You need to turn on some heat in here, or is it cold? No. Okay. You're all right. Okay, let me pump it up a little bit. Yeah. Thermostat's on 65. Yeah. All right. So we used to see some of these motor homes, and when you drive off on this motor home, the doggone fuel gauge would go, or a temp gauge, one of the gauges, it would go up as you were driving off, and when you stop, it would come back down. It was actually like a little miniature speedometer. And the problem with that was they had taken a big old ground wire when they built the motorhome, and it with the big heavy lugs on it, a little short piece of black cable, and like double off, and they would hooked it from the engine to the frame, and every time the engine torqued a little bit, they eventually broke that ground wire, the lug off, and then they didn't have no good ground between the engine and the frame, and that made the gauge read crazy. You got me? So if you got gauges that are doing stupid, crazy things, always see if the engine block is grounded to the frame. One thing you can do is just take a jumper cable or some strong piece of wire that you use for this purpose, hook it to the good solid place on the block where it's clean, hook it to the negative battery terminal or to the body or whatever you're trying to ground, and see if that takes care of it. In some cases, like when the old regulator was mounted on the frame, if you had a bad ground like that, it'd make the alternator overcharge. See what I'm saying? Burn things up. Okay. Switches are necessary to turn the circuit on and off. You've got to have switches to turn it off and on. The load is a device like a bulb or a motor that uses up electricity and turns it into work. You got that? Probably already got that. The circuit protector is a fuse. That's what a fuse looks like on a schematic. It'll kind of look like an S. A circuit breaker will have a sort of a bow shape to it whenever you see that on a schematic. The conductors and components can cause an overload. All right, current will flow. Yeah, the switch is closed. The circuit protector is not open, means the fuse is not blown, and the charge is available. If you got power available from your source. Here's Ohm's law. So jump into Ohm's law here. The basic rule for the relationship between voltage, current, and resistance. Now, in that CDX thing, you're going to see another little thing for calculating watts. Watts is volts times amps. Okay, you got that? So you can basically, there's a little formula for that too. Current flow is directly, there was a pipe loader one time that I was working on, and they wanted to put lights on it. It was a 24 volt system. right? Somebody gives you this job to do, they task you with putting lights on a pipe loader, and all you can find is 12-volt lights. You know, these are actually lights that have got little dome backs on them and all. You have 12-volt lights, but you got to put 12-volt lights on a 24-volt, and they need to be able to be turned on with a switch. How are you going to do that? What's the smartest way to make that happen with the least amount of work?
The 24-volt system still runs off of two 12-volt batteries.
It does, yeah, but they're actually wired in series.
Can't you just wire one battery?
You could, but you're going to have to figure out a way to hook up to this one battery. That's a pain because they got this old big terminal hooked to them, you know. You could make it happen that way. But what I did was, I actually ran the wires into one light, ran a wire to the other light, and then grounded the other light, so the power was going through both 12-volt bulbs. It was in series. See what I'm saying? When you got two 12-volt batteries wired in series, a 24-volt is actually going to push two 12 volts and it won't blow the bulb. Because each one's only using half the voltage.
Wow.
See what I'm saying? All right, so what you do is, the only problem with that is, if you blow one of them, you lose them both.
Yep.
That's the only problem with that.
Okay, before you switch, I'm trying to add this up, so that both of those will be 12 ohms, right?
You got a
Well,
question
we're trying to
on here
find
that
out.
says it's.
No, this is 18 ohms.
Look, you got a question on
Yes,
here
I'm
that
in.
says it's two 6-ohm bulbs are connected in series, they're combined with resistance with how many ohms?
You also have one
If
about
you know what a
parallel.
series or parallel?
There's
In
also,
series,
there's also one for
In series.
parallel.
Yeah.
but in series,
Yeah, in series, you're actually going to add them up. It's easier. Parallel is a little harder to figure the ohms, but it's easy to understand whenever you think about it the right way. This right here, these basically are both wired, and they're wired parallel, because each one has its own ground. That's how you know it's parallel. If each component has its own ground, it's parallel. If it has to go through this one on the way to the other one to ground, that's basically series. I'll show you that in a minute.
So if they have
There's
one
no
ground.
But you're just going to add the resistances up. You got 6, you got 12. That's parallel. Wait a minute.
no.
I'm telling you a lie.
Yeah.
Okay. So here's how this goes. You got me confused, okay? I'm sorry. You know, so sue me. All right, look. What we got here is we got 2 and 1 amp, right? We're pulling 3 amps. 6 and 12. All right, so how do we get that? So how do we get the total in there? How much resistance does this have? Okay, how many volts we got total? We got 12, we got 3, right? Okay, so 3 into 12 equals what?
4.
Okay, so this total circuit has got 4 ohms because they're wired parallel. I'm not really careful when I'm looking at all these circuits. I guess that's screwed up.
That's not
There is a formula for that.
That's not an answer though.
Yeah. Yeah, well, we're gonna get to this. I'm gonna show you the formula of how you get that. You know, but parallel, basically parallel. If you got two 6-ohm bulbs wired parallel, right, and they're both the same, it's gonna be half as much as the 2 6s. It's gonna be 3 ohms.
That's parallel though.
Parallel.
But
If they're in series, you add 6 and 6, and it's 12.
12.
All right. Well, I'm not really careful. I get my own self screwed up on
Okay,
this stuff,
so
but
it's-
it ain't really complicated. But you know, if I'm, when I'm talking up here and people asking questions and I get too close to the picture, I get messed up. Okay, right here, you got that. Look at this. What you got? Current flow, amp. Basically, that's all that slide's telling you is you're gonna call it amps. Look at this. This is a little bit of trivia. If you ever get on Jeopardy, 1 amp is defined as the movement of 1 coulomb of electrons past a given point in 1 second. A coulomb is 1 billion electrons.
1 billion.
A billion electrons. That almost sounds like a national deficit. Yeah, you look it up, it is.
1 billion.
Yeah, billion.
Billion.
Current is a measure of the rate of electrical flow. It can also be known as amperage or draw, and measured with an ammeter. This is the same picture that we've been looking at all this whole time. And you keep on the picture change. When 2 loads are connected parallel, each draws current independently of the other. A draws 2 amps, B draws 1 amp, total 3 amps. Okay. The total parallel circuit equals the sum of individual current draws. Got me?
Okay.
In other words, this was drawing 2, that was drawing 1, 2 and 1 is 3. Got it?
Got it.
Got it. All right. All right, if the same 2 bulbs are connected in series instead of parallel, it's going to be 6 and 12 equals 18. You got that?
2 6.
Everybody got that?
Yeah.
This is in parallel.
All right, now watch this. 0.67 ohms times 18 ohms Amps times 18 ohms equals 12 volts. 12 volts divided by 18 ohms is 0.67. There's your little triangle thing.
But if
think it's
you
gonna pop
lose
up there
one
next.
bulb, you lose them both.
Yeah, see that? Yeah, you'll lose them both there. But that's how you do that, see? If you know what two of those values are, you can figure out what the third one is. All right, there's resistance. Resistance is an opposition to the current flow. What is this? Anybody know what that is?
Why am I thinking that looks like a fan?
Looks like a-
That's a
looks like a
that's a
starter.
rheostat.
Yeah, you dim your headlamps, your dash lights with that.
Oh, cool. That favor there.
Yeah, this right here is a resistor wire. And you got a little contact sliding on it, and the current's flowing through the resistor wire, and the closer you get to where the voltage is being fed, the brighter it gets, and you go down.
Yeah.
That's what a rheostat does. It's similar to a TP sensor, but it's made to pull a load. TP sensor sends a signal. All right. Conductors have some resistance. Listen to this. A 22 gauge copper wire, 60 feet long, has 1 ohm of resistance. Got that? Larger diameter wires have less resistance.
So, the copper does have a little resistance.
Yeah, if you go a long way, you don't have to resistance there. Heat causes resistance to increase the conductor effect. I had an instructor one time that was saying that resistance didn't cause heat, and everybody in the class rolled their eyes. And I took him on that, and I said, look what happens here. You got a volatile relationship here that exists between heat resistance and electrical wiring. This right here is what happens. You start to get a little oxidation between those terminals. They start to build some resistance. That resistance starts to create heat. That heat creates more oxidation, and it snowballs out of control, and finally current quits flowing, and when you unplug the relay, you say, golly, this is a mess. No wonder the blower motor didn't work. High current loads have problems like this when vehicles get old. If a blower motor's not working, a lot of the times it's because you got spade connectors that got hot, right? That's what happens there. When they get hot, every connection has some resistance that produces heat. The more current that's flowing, the more heat it's going to make. That heat produces more resistance, that makes more heat until the current finally stops flowing and the component fails. Okay, when resistors are in series, now listen to this, this is cool. We're going to get into, like we talked a while ago, 6 and 6, 12. That's what you got in your paper right there. Everybody done there. All right, look at parallel though. When they're in parallel, the total resistance equals the source voltage divided by the combined current draw.
Huh?
You talk too fast.
The resistors are in parallel. The total resistance equals the source voltage
Divided by the combined current draw. Remember earlier we were saying it's pulling 3 ohms at 12 volts. We realized it had 4. Even though it was 6 and 12, it was a 4 ohm circuit, right? That's because when you put them parallel. Think about this. What if I've got a bucket? And let's think about the holes I'm going to punch in the side of that bucket. I'm going to drill a hole in the side of the bucket. And I'm going to drill a really small hole in the side of the bucket. You're going to see water start coming out because there's water in the bucket, right? Okay, a small hole, think of that as a lot of resistance. Okay, yeah.
I just got a question about one of the things on the test. Number 16 has the blank of all voltage drops in a circuit always equals the, and then that stops.
Yeah, the source voltage equals the sum of all. In other words, if you've got a circuit, the sum of every voltage drop in it is going to equal the source. That's always the way it works.
Okay.
All right, now then, but what you got here is, I drill, this is a 10 ohm hole. I drill another 10 ohm hole. That's equal to what? A hole twice as big, which would be a 5 ohm hole, right? Think about the size of the holes. How much water is going to flow out of that thing? Twice as much water, which means you got half the resistance. That make sense?
Yeah.
You drill a 10 ohm hole, you drill another 10 ohm hole. If you drill another one, it's like a 3.3 ohm hole, because you got 3 times as much water coming out now, which means you got less resistance. It makes sense. That's the best way I can say that, where you can grab it with your head. Now there is some equation stuff going on here. See that? With a 12 volt supply. Are you guys getting smacked around by that?
A lot. Alright, so 12 volts and you got 2
All right, let me ask you this. I got 12 volts, I got 6 ohms. What's 12 divided by 6?
2.
Okay, I got another 6 ohms. What's 12 divided by that 6?
2.
What's 2 and 2?
3.
It's going to pull 4 amps. Each one's going to pull 2 amps, because you got an additional current path. So it's a 4 ohm thing, right?
It's a 4 amp system.
Is that true?
These are the electrical.
I mean, are we right about that? 12 volts,
Yeah.
we got two,
They-
2, be a 4 amp.
I could see if it had 2 grounds,
Huh?
but it's only got 1.
It's only got 1 ground, that's right.
If it had 2 grounds, it would be 4 amps.
Yeah. 12 volts, 2 amps, 6 ohms. Each resistor will pull 2 amps, 2 and 2 is 4.
Okay,
Got it?
sure.
Alright, so if the total circuit pulls 4 amps, how many ohms of resistance would the total circuit have based on a 12 volt supply? 3.
Hang on, time out.
Back it up.
All right.
If the total circuit pulls 4 amps,
How many ohms of resistance would total?
and you know it's
circuit
12 volts, so 12 divided by 4 is what?
have? 3.
Okay, that's good.
I like that.
There you go.
Yeah,
All right.
that's what I was on my tip for.
Okay, let's try a different combination. With a 12 volt source, how much total resistance would this parallel circuit have?
All right, hang on a second. Now we're getting somewhere. All right. So you get 12 volts, 4 ohms. You're looking at 3 amps. 12 volts and 6 amps, or 12 volts and 6 ohms, you're looking at 2 amps. So 2 and 3 is 5.
Yeah, so what is what's
That's what I say.
yeah, what's 4 and 6?
4 and 6 is 10.
Yeah, 4 and 6 is 10. Okay, now what's 6 divided by 4?
16
By
by
6
4.
by 4.
Yeah,
1,
That's
2, 3.
yeah.
You can.
Well, you can, but, I mean, it's not getting what we want.
Let's look and see how this works. Look. All right.
12 divided by,
5 amps, 2.4 ohms.
See, I got the amps. I just
okay,
didn't
so
get the ohms.
then, so we got the amps, which was
If
5.
see if they were both the same, remember this, it was 6 and 6, it wound up being 3 ohms.
Can you go
I
back
know,
to
but see, we had
slides?
4, and then we had 3, and that 5 gave us that, but we should have divided the 12 by the 5 and got the 2.5, right?
Yeah. So basically,
This is what you do. You're trying to get the individual amps,
If you get
right?
amps.
yeah, if they're,
So-
yeah. And you can do that, you can figure it out that way,
You've got
yeah.
3 and you've got 2. So that's why I was saying 5 amps total, right?
Yeah,
And then you do it again to get the total ohms. So you go 12 divided by 5.
yeah.
And that's how you got that weird loopy number.
Yeah, it won't always be an exact amount, that's 2.4, okay? That's resistance in
And see, what I was
parallel.
doing is I was
That's in
adding
parallel.
up.
Resistance in parallel is figured that way. Now, let me tell you this. This is something that everybody that teaches electrical stuff teaches. And so you're going to see this everywhere you go. If you ever go to electrical school or you work in a dealership, you're going to hear the same thing, basically. You're never going to use this to fix a car. You're just not. I mean, I'm not saying you don't need to learn it, but I'm just saying that if you can get so focused on this right here and it can scare you to death, you know. But if you, I mean, I've never used it fixing a car. You know what I mean? But I mean, it's something you got to teach. Okay, now, look at here. It's a rule for closed circuit. The voltage used up or dropped in the loads must be equal to source voltage. It always is. See, this right here, 12 volts, source voltage. You go from here to here. Or obviously, if you check both sides of a light bulb when it's burning, you're going to see 12 volts. Right? That's just all there is to that. Okay, voltage measure with respect. The voltmeter at point A will measure the source voltage. Okay, you're grounded to here. Voltage measurement is taken at point B, what will the voltage be?
See,
Hang on.
if it's a drop, right?
0.
0?
You measure the voltage on the ground side, you're not going to see
Oh.
anything. Got me? All right. You'd be right. The voltage drop is equal to 12 times 0, which comes to 0 volts. Okay, when 2 or more loads are in series, now listen to this. This is important. So don't let your eyes glaze over. Don't turn into a skeleton on me. Okay?
Oh, too late.
When 2 or more loads are in series, the voltage drop of each load is equal to current draw times resistance. Now this is starting to get confusing, isn't it? But all you have to think about is the fact that I've got 12 volts here, right?
Yes.
Okay, so I want to actually go down this circuit and I want to see what the voltage is as we get closer to ground. All right, the sum of all voltage drop equals source voltage. Look at this, Joe.
No.
See that? That was the answer to the question you were asking. That's closer. You move closer, you move your probe to the ground side of the circuit, the lower the volts go. See that?
Over it.
That's 6 volts. Yeah.
The question I was asking is, why was the question stopping at?
Oh, it screwed up. It was a question that I wrote and I messed it up. All right, see that? You got 0 volts. All right, now let's move our meter again. See? 12, 6, 0. So you're going to be dropping some. Now, the cool thing about voltage drop is, and Melissa, we found on that car the other day, You turn on the key, that Impala over there, and what did you see on the inside? You said it was a bunch of stuff wasn't working.
Oh, yeah, it would flash and click.
Whole lot of stuff that was clicking and not working and all that kind of stuff. And we measured voltage drop between the positive battery terminal and that big lug on the fuse panel. And we were measuring 7 volts of voltage drop. Something's being lost somewhere. Alright, so let's go on. Here's the example shown here. Total resistance is 6 ohm, current draws 2 amps. Right? The voltage drop in the brightness control, which is that little rheostat we were talking about, is 2 amps and 3 ohms, which equals 6 volts. And the only thing the bulb's going to see is 6 volts. It's going to burn half as bright. Which the rest of this is going to be converted to heat, and it ain't going to make it because you got a resistor there. That's what that little zigzag is a resistor. Yeah. Computing parallel resistances by formula. See, that came from a live wire. All right, you got that?
Sure.
How much is that one?
I have no idea. I have to read that.
6.
Look. RT equal R over the number of resistors.
4. 3.
What's RT?
Total resistance. 12 divided by 4. 3.
4.
9-volt battery.
Yeah, that's basically how that thing defaults whenever I do one of those. I meant to make it 12 volts.
So they're gonna be like a 2.5.
All right, if all the resistances are equal, divide the resistance of one alone by the number. If all of them are the same, and all of these are 12s. Okay.
That's 3.
Yeah, this is 48, 4 into that. Yeah. So what? I told you this, if you read the instructions, which we got off base here, that's 48 if it's in series, but if this is in parallel, you're going to say 4 into one of these is what?
3.
So that whole thing's going to be 3 ohms. 12 over 4. See that? 3 ohms resistance. If there's only 2 resistances, you're going to multiply their values and divide by the sum. Does that make sense?
6 times
Watch
12.
this.
Someone
Yeah.
needs to have to-
You're going to say 6 times 12 is what? What's 6 times 12? 72 divided by 6 plus 12.
18.
Yeah. What's 18 into 72?
A lot.
Sure is.
Yeah. 18 into 72. Let me guess.
4.
Yeah. There you go.
But I'll take
Okay,
it.
so you got 4 ohms there, 6 themselves. See that? 18 into 72. Is that right?
Yes.
Yeah.
All right. For any 3 or more, find their reciprocals, then add the reciprocals together and find the total power. See, as you go up, this gets more complicated. You know, and you can burn a lot of time on this if you want to. I went to Ford school one time. The first time I ever ran into this long years ago was they had a bunch of, they had a parallel thing, and they said, and it was a multiple choice thing. They said, how much does this have? You didn't have to do any math. It's always going to be less than the lowest. See what I'm saying? Like if you've got a 10 ohm, a 5 ohm, and a 3 ohm, it's always going to be less than the 3 ohm. It has to be. You see? So it's going to be, and one of the answers is 1 or 2. It's always going to be the 1 or the 2. You don't have to really do any math. You just have to be, So here's how you do that. Okay. Plus 1 over 5, that's 0.2. Okay, 1 over 4, quarter. 1 over 12, 0.083. Okay, so you're going to take 0.2 plus 0.25 plus 0.83 equals 0.533. Okay, you got 1.88 ohms per line of resistance. I'm not going to spend a lot of time on that because your eyes will glaze over.
They glazed.
That's what I'm saying. All right, let's jump past all that. I mean, like I don't point. I see no point in going through all that. I mean, there's some places they really go into that heavy. Power sources and ground. You may run into something like that on CDX too. So just be prepared for it. Power sources and grounds. Right there. You see that? Now look at that. What are we looking at over there? What kind of deal is that?
There's an open switch.
Maybe, but the long and the short of it is, you got 12 volts feeding this switch, which is going to operate that solenoid, right? And then you basically are coming over here This one here, off, nothing happens. This right here, through a resistor, this motor's gonna have as fast on that speed as it is over there.
Yeah, because it doesn't have the resistance.
As long as you understand how that kind of stuff works, you're gonna do pretty well. Okay, there's your battery. Generator maintains the charge in the battery after the engine started and supplies electrical current. Now these right here, what are these little things right here, guys?
Diodes.
They're diodes, and what is this part?
That's yours. I want to say it's a stator.
That is actually the stator, and this right here is the rotor, right here.
I mean, motorcycles are separate.
Yeah, it's really interesting how they draw that. But anyway, I drew you a picture of what it looks like on a schematic.
This is close enough.
Case ground. Some relays, the housing of the relay is actually the ground. So when it mounts to the body of the car, that's going to provide the ground for the relay coil. And like some of your light bulbs are like that. Okay, remote grounds means you got a wire coming from the component to the ground somewhere else. Okay, ground's used to control the components, like going through the switch. You know, power windows, door locks, they have a ground that goes through the switch to control them. You'll read a schematic here. Okay, we got to be able to read a map of the wiring. Got to be able to cross-reference the schematic with the physical wire harness on the vehicle itself. And we're going to have to be able to use the component locator function built into the shop manual so we can find the components. If I know that I've got a problem at a particular component or connector or whatever, maybe it's throwing me a trouble code, or maybe my troubleshooting is taking me to that point, I've got to be able to find out where that thing is on the car. I'm going to find out this inline connector in the harness has to be what the problem is. I'm going to pull up the locator, and it's going to tell me where that component is, and I'm going to go to that connector, I'm going to unplug it, and I'm going to know what color wire it is and what pin it is to show you how to do that. This is some of the basic stuff, and that's why it's just taking a while. All right, now this right here, we're not using this software anymore, although it is on some of the machines. And I'm going to show you this. We're going to choose a schematic point of view, and this is giving you some navigation stuff. Okay, the top of most schematics is usually hot, and the bottom is usually ground. Remember that. You going to remember that?
Yeah.
The top of most schematics is usually hot, and the bottom is usually ground. Power is fed to the fuse. Thus trace the power from hot to ground through circuit 295. Look at your circuit number. The circuit number is important. 295. And connector C172. See that?
Yeah.
The male side of the connector is C172M. The female side, and I spell that wrong, is C172. Okay, where's connector C172? We know that we've got a problem between point A and point B. What connectors are located between the component that's not working and the power that feeds it? We've checked our fuse. It's there. There's no power at whatever this is feeding. We know this is the only connector in there. Now, when you see a broken wire like that right there, that means that this wire is going other places besides here. Now, this right here is an alternate current path. And what that means is, on a manual transmission car, it goes this way. On an automatic transmission car, it goes that way. You see that? You got me?
Okay.
Now, the wire's the same color, but if you see an alternate current path, that means this wire is going to go and do the same job no matter what. Okay, but it's basically, that's an alternate current path. And right here, you see the connector is basically going in the wire like that. Yes. Now then, most wiring books have something that looks similar to this, right? Okay, do you see, what do you see? Do you see 172 on there?
172.
C172. Connector C172 is where?
We're going.
Yeah, C172 at the top.
Right up there.
Oh, there it is.
Right there.
Yeah.
Now you know that you said that connector is between the fuse that's lit up and the component that's not working. Now I need to know, all right, now I'm going to look at this map, but you can find that if you look at connector views.
Yeah.
All right, I'm going to remember my circuit number. C172F is on the left and C172M is on the right. These two plug into one another. They're mirror images of each other. You see how these black pins don't have anything in them? All right, these are mating connectors, and these right here are your circuit numbers. The circuit numbers are really important. These are your colors, light blue, black, red, white, black, gray, white, blah, blah, blah. All right, circuit 295 is where? Because that's the circuit we're concerned about.
Let's see.
Where's circuit 295?
Right here, light blue.
Light blue, pink.
Pin 34.
There you go, pin 34. All right. Now then, now that we know that, we know exactly where to go, see? Now we not only know where C172 is on the vehicle, we also know what the connector pinout looks like. That way we can tell if we're on the right connector. In other words, if I think I'm going to C172 and unplug it, it's only got 3 wires, I know I'm not in the right place, right? All right, we also know what the connector pinout looks like, and we know that pin 34 is the one we need to be concerned about. Got me? That's how you troubleshoot and find out what's wrong. There's three things we ought to notice about this current path. The truck can have either two switches, depending on whether it's manual or automatic transmission. That's drawn as an alternate current path. That's what we had before, is what I told you. See? And that's the same circuit, but it's, I'll show you the rest of it. So you got a torque neutral switch. All right, now what does this do? What's the purpose of that? What does that circuit do?
What?
Oh, that's
Turn
the.
lights on?
Backup lamps.
That's the.
The backup lamps are turned on by
Turns
the
on the reverse.
neutral safety switch on the other. And see, you got, and when you see a dotted line like this right here, that means that both of those, like for instance,
That's where they reach over.
well, basically, this is an alternate current path, but if you ever see dotted lines like that when it's not an alternate current path, it means they're going through the same connector. Got me? All right. The wires going into and out of the switch both pass through connector 172. Both of them go through the same connector. See that? All right. After the circuit passes through the switch, the circuit number changes from 295 to 140. The circuit number changes when it goes through the switch. See that? We're doing the same job, but now we've got a different circuit number because it's. All right. Let's look at the connector pin out. Circuit 140. Which one?
32. Pin 32.
Yeah. Pin 32. Got it? All right. There we go. Now we know pins 32, 34, and 32 are both part of the backup lamp circuit, and either pin could be the cause of the problem.
That's the in and out.
Now, is this a sensible lesson that I'm teaching you right here? This is how you learn how to fix stuff. Okay? Now the circuit passes through a splice and two more connectors. The splice could be the problem, but it's usually taped into the harness and it's difficult to locate. The splice is the last thing I check. Because it may be way up under the dash, in a harness as big around my wrist, right up in the middle. That's the last thing I'm going to look at.
And it's just basically a Y.
It's basically, not only that, it may have a bunch of wires going in there just, heat crimped together and have heat shrink over it. You'll see that, all right, so or have cloth tape over it. But right here, let's watch this. Let's find the connector C148 on our location. This one right here is the next one we're going to look at. Right? Okay, where's C148?
Right there.
See D10 on the grid?
It's over by the headlight.
D10, 148, okay. This pinout legend is a little different. Find circuit 140 and double check the wire color to make sure we're still on track.
Pin 13.
Yeah,
Bottom
okay.
corner.
Once again, we can find the connector on the vehicle, locate the pin on that connector so we can check the integrity of the circuit. When I'm going to a relay or anything and I'm not exactly sure what's what, I'm going to see this relay has this 5 wires and they're these colors. Does this relay have 5 wires that are this color? That keeps you from going off the rails. Make sure you pay attention to the color of the wire and watch the connector and all that, and you can make sure that you're on the right one. Because if you get off track and you get on the wrong wire, you can cause all kind of problems for yourself. Make darn sure you double check everything.
You definitely cut the wrong wire.
Yes. So now let's go and find C411 the same way. See, we've still got backup lights that aren't working. We're still trying to track it down. Where's
C411's right there.
Right there. C411 is
Yeah,
way back in the
it's
back.
right there.
See there? Now on your schematic it looks like it's just right here. You notice that? But on the truck it's on the opposite ends of the vehicle. The circuit number we're looking for is still 140. Find it right down the pin number. Where is it?
It's top corner.
5.
Black
Looks
pink.
like 5.
Yeah.
Pin
All right,
one.
you got that?
5.
Okay.
On the right.
Our last inline connector is C403. Let's find it on the vehicle like we did the other. Right? That's the last one. That's the last one it can be. We know we're getting power all that way. E10. Where's
It's
E10?
in red.
Yeah. E10. C403. All right. Look at that. You notice how the closer we get, the fewer wires we find in the connector. All right. There's one. The circuit number is still 140. Find it here. Write it down. Once again, we go back to the connector on the vehicle, find the pin in question, and check the circuit. By this time, we ought to have more of a handle where the problem is. We're actually narrowing it down to do it the right way. One more potential problem is the ground. G104 could be the problem. So the light's not working. Let's locate that. Where's G104?
about 10 right there.
What? The backup light ground is up here in the front? What the heck is this? But that's really crazy. That's a bunch of hooey. That's what they stuff it up there in the front, right? You got me?
They just wanna mess with people.
Yeah.
And you can't fix this, take it to the dealer.
Yeah. On the schematic, the ground looks close. See that? However, look at all these little broken.
And it's got a splice.
It goes other places besides just to that one place. See, it's not just, there's other things it does. All right, the brown for the backup lights off and in the vehicle. All right, now on your GM, they're a little different. See that? Here's a schematic representation of the vehicle speed sensor. GM has hot buttons on their schematics. All right, basically, you're going to look right now. They're a little harder in the GM to find. You actually got to go here, engine controls component views, engine controls connector end views. See how you got those little things you check?
Uh-huh.
All right. And this one here doesn't go as long. All right, so 4L80 transmission. See? Well, remember, we're looking at vehicle speed sensor. Now you're actually going to be looking at that when you click on that, and it's going to show you where the sensor is in a very similar way to do that line arc. Yeah, that's it. See how quick that was? I wasn't going to spend a lot of time on that, on the last part of that, because you already had the idea.
It's about a cylinder on it, does it?
Huh?